got his PhD from Vanderbilt. He was then a postdoc in Illinois, then University of Chicago, which is where I think I met you.
Yep.
First.
Yep.
He did some very nice work there related to verification and validation of simulations involving type of supernovae. He then went to Stony Brook, where he's now a deputy director for Institute for Advanced Computing.
Computational science.
Computational science, sorry, computational science. Let's see. What is the society a member of?
The Joseph Sheffield Memorial Society.
Members of the Joseph Sheffield Memorial Society, which involves a bar in Sheffield Avenue in Chicago. Let's see. Yeah, that's it.
Okay. On that. Well, I'm.
There are a lot of legendaries. You are legendary. You are legendary in certain areas. So.
Well, let's
Astrophysics being one of them.
well, let's hope the astrophysics is one of them. Yeah, yeah.
But he's going to tell us about his quantification, uncertainty, and astrophysical simulation.
Okay. Well, thank you for having me, and thank you for everybody that I've spent time with. This has been an absolutely delightful visit, and I love the tour of the multiple experimental rooms and facilities I saw. It was absolutely wonderful. And for the students, the lesson of the Joseph Sheffield Memorial Society, there's a bar in Chicago called Sheffield's, and they have a very fine beer selection. I mean, really nice. It's a nice way to explore nice imported things. I had lambic beers for the first time. And you keep a card, and as you work through the list, you're inducted to the society. And I put that on my CV in approximately 2001 as an honor and an award, and it's still there. And in no interview has anyone ever asked me what that was. So I'm not sure of the lesson there, but just don't be shy about putting fun things on your CV if you're. So Melissa Hoffman was a graduate student who is now taking a position doing data analysis at the National Radio Astronomical Observatory, and this is her master's thesis work that I'm presenting. This is me, Alan Calder at stonybrook.edu. If you have any burning questions or criticism that we don't get to in the talk, feel free to write and ask me some questions. Don Wilcox and Matt Katz were grad students. Don is still there. Max is now at NVIDIA. Doug Sweste's a research associate professor. And Scott Ferson, who's now at Liverpool, was at Stony Brook, and he is an expert in uncertainty quantification. And what I'm going to tell you about, I'm going to tell you a little bit about the problem that we work on, and I'm going to tell you about these two approaches that we got from the uncertainty quantification literature and applied to the type 1a supernova problem. And I hope the story of these attacks on the complicated problem of a very large number of parameters, although I'm only going to show a couple, but a very large number of parameters that you can then meaningfully try to assess how that affects the bounds of your results. And that's the main story I want to tell. So I covered that. I'll talk a little bit about some of our supernova stuff. I'll introduce that. And particularly, we're interested in systematic effects on the brightness of an event. And that's where the uncertainty comes in, because if you have something that slightly changes the brightness, how do you know that it's not just an effect of a model parameter or something like that? And then I'll go into the uncertainty quantification, and there are two what I'll call advanced approaches, which basically means something beyond just brute force. And I'll step through how we did that for the problem of creating a white dwarf with the MESA Modules for Stellar Astrophysics code. Okay, so any questions, fair game as we're going along. Please, if there's something that I describe, you never heard the vocabulary, don't be the least bit shy about asking it. I'll try to save some time at the end, but if we go in runtime, it's usually better. So a supernova is the explosive death of a star. These things occur something like 30 times a second in the observable universe, which translates to every 50 to 100 years in our galaxy. For many, many years, we thought there was something missing because the only supernovae we had go back to Tycho and Kepler. But then this thing was observed. The blue is a radio observation in like 1985 or something, and the red is a Chandra X-ray observation, and this was something that would have been observed, depending on which news article you read, 140 years ago or 110 years ago, but it was toward the center of the galaxy, and we didn't see it because it was obscured by dust, but you could see it in radio and X-rays, and from the rapid expansion from this thing to this thing, we know that it was a fairly young thing that we would have seen roughly 100 years ago. And of these things, about 80% are core collapse, a very massive star, and its core fuses all the way to iron group stuff. There's no longer energetically favorable to fuse. So you get this inert core, and eventually gravity wins, and it collapses, and anything beyond that, ash on. And others here too. So what do we see? Here, we have a simulated supernova going off in a different galaxy. And this is a 1A, which is the thermonuclear case. The 1A is a spectral identification that was supposed to loop. But you see the light curve rise over a relatively short period of time, that's days, and then decline over weeks to perhaps months. And of course, if you look at the spectrum, then from that you can discern what is in there. And these thermonuclear supernovae are interesting. This is the standard slide everybody who gives a 1A talk shows, but they're very bright. The brightness rivals that of the host galaxy, something like 10 to the 43 ergs per second. Not as bright as the host galaxy, but it rivals it. And they produce, they synthesize large amounts of radioactive nickel-56, and it's the decay of this into cobalt and into iron that produces gamma rays that go on to power the light curve. They occur less frequently than the core collapse, and there's no compact remnant. If you want to get a black hole or a neutron star that comes out of the core collapse, this completely disrupts the progenitor white dwarf. And the key is that there's a very robust pattern in the light curves, and that is, this is magnitude versus time, where the 0 is the maximum. You can start the clock. The brighter supernovae, which are these curves up here, decline less rapidly, and that's known as the Phillips relation. You can see in the change over 15 days in the B-band magnitude. You can see this one is steeper. So there's a one-parameter relationship we call a stretch, that the brighter ones are broader, and you can then calibrate that, and that gets you a standardizable, or it is a standardizable candle that you can then use for cosmological measurements as distance indicators. And it turns out that in so doing, the best fit is to a universe that's about 75% dark energy, and that was, of course, the discovery that led to the Nobel Prize fairly recently using these standardized candles. And this is a pretty good fit, but even if you subtract off the expansion of the universe, and that's this plot here, there is still some scatter about the Hubble law. We call that the Hubble residual, and one of the questions we have is, what is the intrinsic scatter of these things? And there are several things that could come from. I showed you the schematic where the supernova goes off in another galaxy. It could be that there is dust in the galaxy. It could be that there are different ages within, or different galaxies are of different ages. That would, the environment and metallicity could lead to a population drift with redshift, or there could be different evolutionary channels for these things. And so I'm tearing through this. Everybody good? Any questions? Oh, cool. All right. Please don't be the least bit shy. I know there's a lot of vocabulary, but so good so far. All right. Well, there could be different evolutionary channels, and there are three principal models under investigation for these things. There's a so-called single degenerate Chandrasekhar mass model, which involves a single degenerate star, a white dwarf, that has gained mass from a companion, and as it approaches this Chandrasekhar limit, beyond that, it will begin to collapse, and then electron captures will go, and you'll get a neutron star. But before that happens, at the high densities and high temperatures, carbon fusion goes, and that ignites as this thing approaches the limiting mass, and we call that the single degenerate case. You can also consider merging white dwarf pairs, and these can violently collide or gently merge, and people are exploring that. And they may explain some very bright events, because instead of one white dwarf, you've got two. So you may be able to synthesize more radioactive nickel, and some observations imply that there had to be more nickel than you could get from a single white dwarf. And then there's another model that I believe folks here are still working on. I know Adam was playing with that for a little bit. But that's the so-called sub-Chandrasekhar, where you have an accretion problem like this, But a detonation in the accreted shell triggers shock waves that leads to a detonation in the underlying white dwarf. And because the white dwarf is smaller, that may explain some dimmer events, but none of these has won the battle. There's reasons for and against all of them. I think currently people are most interested in the merging white dwarf pairs and this, but Chandrasekhar hasn't been ruled out, and that's what we've been working on. So how do you make one of these things? Well, you've got two stars. This is the Wikipedia version of it. You've got two stars, one a little bit more massive than the other. It goes through a giant phase. Eventually there's a common envelope point, and you have a white dwarf orbiting another main sequence star after they've cast off some mass. And then here you have this white dwarf just orbiting, and we can say that it's isolated and that it can cool there. And I'm going to come back to why that's important. The aging companion then becomes a white dwarf, then becomes a red giant, and then accretes material onto the white dwarf that approaches the Chandrasekhar limit. It starts the fusion process that incinerates the star, and boom. And we would think that the companion would be shooting off somewhere, but we have yet to find reliable observational evidence of a peculiar velocity of a star that would suggest that. Now, without going into a huge amount of detail, this is the way that we blow one of these things up. And I thought it was worth explaining my model to show how slight changes in things can affect the result. So this is a 2D simulation where this part in here in white is the initial match head, where we're assuming that there's some sort of turbulent combustion that has happened and burned so much material here. This is all within the star, but this threshold here is a certain density, say 5 times 10 to the 7 grams per cubic centimeter, where this initial deflagration down here is going to transition to a detonation. Now, I know what you're saying. Okay, wait a minute, aren't those the same thing? Well, a deflagration means it's subsonic. The burning is not faster than the speed of sound, and the key is the star can react, and it's going to expand. And then when the detonation goes off, the amount of expansion determines how much material is at a high enough density to then synthesize the iron group stuff and the nickel-56 in particular. So it's interesting, but the timing of that transition as the star is expanding is one of the very critical knobs of how you determine the yield from one of these things. So here, let's take a look at that. All right, so we perturbed it. It's a perturbed spheroid, and we stayed away from the edge because it'll just shoot up because of the boundary conditions. But here this deflagration goes, and there's turbulence going on. We think there's Rayleigh-Taylor instability on unresolved scales, and at some point we think physically it's going to transition, and we just give it a little kick, and boom, there goes your detonation. There's a second one down here.
When you say give it a kick, do you assist it in some way? Or
Yeah, basically we declare that there's a certain size that we just burn, and it goes. And for the purists in here, it's a race between this rising bubble generating Rayleigh-Taylor instabilities and the burning fire polishing. And at the lower densities, the Rayleigh-Taylor instabilities kind of win, and this thing gets all twisted up. And depending on who you talk to, it reaches a certain critical fractal dimension, or a pocket of fuel gets wrapped and the Dulvich mechanism happens. But that's on scales we can't resolve in that. So indeed, we just choose, once the bubble hits a certain density, we just burn a little bit, and the code is able to propagate. It's a self-sustaining shock that propagates through as a detonation. Now, here's the same simulation, the same initial match head, everything else, but we're going to look at the variable that controls not the consumption of carbon that we saw before, but the relaxation into the iron group elements, some of which are going to be the nickel-56 that produces the light curve. So here, this should look exactly the same. You've got this slow deflagration, all these fluid instabilities develop, and on the subgrid scales, indeed, this thing is getting wrinkled up, and we assume that at some point it's going to transition. Notice the star is expanding. You see the scale is changing. But, boom, in this case, there goes the shock, but you only burn into the higher density regions, and that shows how that dial works. If I had changed that threshold density for the transition, then depending on whether it was higher or lower, the detonation would have occurred earlier or later, and that would say how much of the star had expanded, and thus how much iron group elements you would get. Everybody see the logic of that? So I'm going through this pretty quickly, but I'll show you an example of a result that we found. This is a set of simulations where a realization is a set of random numbers that determine that perturbation. You remember the little spiky sort of perturbed sphere in the center. And here we just took a progenitor model that was a parameterized thing. It wasn't just a cold white dwarf, but it had a shift in the carbon abundance to account for slow simmering going on in. And we just cranked the progenitor central density up from 1 to 5 times 10 to the 9 grams per cubic centimeter, and then just repeated each of those realizations, that's the match head, at each density. And as you can see, this is the nickel-56 mass that decreases with central density. But if you look at a given realization, there's an awful lot of noise in there. If you just did these two, you would conclude, oh, well, as you increase the progenitor central density, you increase the nickel production. If you run a whole bunch of these things, you see a definite trend like this. And the reason for it is that at the higher densities, the electron capture rates are faster, and you neutronize, and you don't produce as much nickel-56 when the detonation goes through. Even though you're burning as much mass or something like that, you don't produce as much nickel-56. Yes, yes. In this case, now we also varied that, but that's another knob. But yeah, everything's the same except that central density. Yes. You make things like nickel-62, which is stable, and then you don't get a light curve. It's the nickel-50. And thank you for that question. I should have made that crystal clear. But you're producing roughly the same yield of iron group stuff, but it's all neutron rich and it doesn't decay. So you don't get a bright display, and so we can directly correlate that with the brightness of the light curve. So let's go back to our formation of this thing. I said that the time in which these guys just orbit without any mass transfer is important because this white dwarf is just cooling. And it can cool over giga-years, or maybe a small number of giga-years, but and eventually crystallize and things like that. I have a busy slide I'm going to throw up, but I'm going to tell the story first, and then I'll make sure I got it right. But the logic is that the cooler this thing gets, once the accretion occurs, it is compressed and it heats up again, but the model remembers it. The white dwarf knows that it got cool, and the central density is higher when you get near the Chandrasekhar mass than with the models that didn't have the long cooling period. So what does that say? Well, that says that the time scale up here is set by the main sequence age of the stars. This is set by like initially how separated they were, because it takes a while, gravitational radiation and other things to bring them in. So this is a knob that you can turn, that separation, to control the cooling time, to control the central density, and it's an age. So here, I've got a busy slide that says all that. Pierre Le Chaffre was the one that showed that an initially cooler white dwarf has a higher central density when the core reaches ignition temperature. And we find that the neutralization produces less nickel-56. So an older population, the only way you could get to be older is the main sequence ages are going to be roughly the same, but that longer separation time, and that's in agreement with some of the observations. And so here we've got an age where this curve is our results, where we took Le Chaffre's work and turned the central density into an age of cooling. And then here we added a range of main sequence ages. And then this is the work of Neal et al. Observational. There are only 3 bins, and it's not very nice to look at statistically. But it does show an overall trend of decreasing brightness, and there's a simple relationship that goes from the light curve to the mass of the nickel-56 with age. Question? It's still pretty warm. I don't know, 10 to the 6 Kelvin, 10 to the 5, Ed, when does it crystallize? 10 to the, closer to 10 to the 7? Okay. Well, it's 10 to the 9 when it's born, right? But, oh, the central density, yeah, yeah. 10 to the 7, 10 to the 8 Kelvin, so it's still pretty hot, but it'll crystallize. But, aha. So you can. We don't. We just controlled for just a non-rotating, carbon depleted, you know, advanced model, but we just changed the central density. Question?
No, I'm just going to control you.
Oh, go for it. Oh yes. So Sean is already pointing out, any question in astro, ask about magnetic fields, and that trips the speaker. Okay, that's one example of what we've done. And here's another of these new hybrid progenitors. Now, forgive me for looking at notes, but I want to make sure I get this straight. JINA-CEE et al., using the MESA code and some other things, came to the conclusion that there may be a class of hybrid white dwarfs. Normally, and I didn't say this earlier, but it's carbon and oxygen that can form the supernova. Oxygen, neon, the star will collapse before fusion can begin. But you can get a class where this curve, the black solid, is carbon, the magenta here is 24 magnesium, the green is 23 sodium. But you can have a convective region that's shell burning that leads to unburned carbon in the core and a lot more oxygen and neon. That's this one, and let's see, the neon is the dot dashed red and the oxygen is the blue. So you still have a lot of carbon, but not so much further out. This is the abundance out here. So why is that important? Well, in the single degenerate paradigm, you have to accrete onto this thing and approach the Chandrasekhar limit. But the more massive neutron stars tend toward the oxygen neon. So if you get a hybrid, you can get a more massive star and you have to accrete less. And steady accretion for, say, 4/10 of a solar mass is a tricky problem. But if you can get closer to that, then it is less of an issue. So we had Don Wilcox doing a series of detonation calculations. This is carbon and oxygen here. There's some 20 neon here representing metallicity. He looked at how the burning, we modified the module in the code that we use. It's the Flash code developed at the University of Chicago to take this problem on. And if you start with one of these, I like to refer to it as a delicious carbon or oxygen neon white dwarf with a soft carbon nougat core. But if you take one of these things and then accrete it, you wind up with a temperature structure that looks like this. It is carbon depleted in the core, it mixes, but the hot spot is out here. The density profile looks very much like a traditional star. There's only a slight little difference. But we think it would ignite, something like this. So we ran simulations where we ignited at some radius out here, and we broke the symmetry on it a little bit. And we did the same DDT simulations at just a different ignition condition. And we found that the pink with the gold is the normal carbon oxygen, and the range is given by like 1 standard deviation of our results. The CONE, those are the hybrid carbon oxygen neon ones. We found that on average, they yield or produce less nickel-56. This is an estimated mass. There's a lot more scatter, but that's actually good because one of the limitations of these single degenerate models is that it's very hard to burn at low densities, and you tend to keep the star, to make it blow up, you have to have fairly high densities. You get a lot of nickel-56. So this is actually going in the right direction. But notice this little bump here. That was a strange feature. And what we found is that it takes a while for that inner region that was cold to be consumed. And you can actually see that in the production of the nickel, that you get a little, there's a delay while that gets consumed and stuff like that.
To what extent does that have to do with your initial conditions? Like if you only had one point of ignition on the surface or something, how would that affect
So
the shape?
that is a good question, and the answer is that it could be so different. I wouldn't have any faith in just one simulation from one point. Okay, what we have done is a suite of simulations where you look at a statistical average of it. So a given event, I really don't know what I mean. What I'm saying is that on average you produce less nickel. That's yeah. Well, I mean, we tried various themes. I mean, this represents like 150 simulations. We tried various themes where we well, that was my fault, so I'm sorry. But does that answer the question now? I mean, I didn't explain it, but this is one example where you ignite at that hot spot and then you just make little perturbations. We change the size and mass and distribution of those things and stuff like that. And you probably are pointing out one thing that, I showed you that initial burned region in the interior, that it's a little hard to go from a few sparks to that, and we kind of wave the magic wand of turbulent combustion, blah, blah, blah. But this is actually a little bit better, too. I think that there's a chance that these hybrid models, if they exist, could answer some questions. Yes, question?
Yeah, what would the axis of that graph?
So this is radius, and this is z, and it's a cylindrical symmetry. The center of the star is here, and this is a radial hot zone corresponding to this, where this is a mass coordinate, but the higher temperature is out beyond the very inner core. And I apologize for not going through that clearly.
Well, what, I don't understand cylindrical
Well, the star is a sphere, but we're essentially, you can imagine averaging azimuthally and then just looking at half of that. So if you have a bubble that rises out, it's actually a torus, and if one rises up the z-axis, it's a sphere because the symmetry is around like that, and we just do half of it. Does that answer the question? Not really. Well, so this plot, you mean? Whoops.
I think it's maybe Y cylindrical symmetry instead of sphere.
It's not. Yeah, it's Z cylinder. But this is the Z-axis up here, and the star, it would be like this. Does that help?
Is the z-axis along the axis?
Yes. 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 This is the North Pole up here, and this would be the radius and the. Good. Thank you. Thank you. Okay. So, cool. I got through an awful lot of stuff there. I just wanted to give you a flavor of the type of things that we're trying to figure out, and in particular.
But in the end, you want to ask what is the effect of the Phillips relationship? Is that the final?
Bingo. Bingo. If we go back here. We want to know what's the intrinsic scatter of these things, because then when they used them as the standard candles, that greatly reduces the uncertainty in the cosmology. And I'm not quite to the Phillips relation yet. That's where it's going. But we want to try to understand just what makes some brighter than others. And the Phillips relation is the standardization of that. That's an excellent question. Thank you. Okay, so what we're looking for is a systematic effect, and what we want to know is how well do we know the things that we think we know before we go and blame something like central density for the change in the brightness of one of these things. So Scott Fersen, who's a collaborator there, twice taught a class, once in the marine sciences department and once in an engineering department on uncertainty quantification. And I sat in it on both times. And by the second pass, I began to understand some of this stuff. And thankfully, he helped us. But I learned a little bit about this. There's two types of uncertainty that people talk about: an aleatory uncertainty or variability. And that's where things are randomly distributed in some way, and you can characterize that. And an example of that is the initial mass function that shows how many stars you would expect as a function of their initial mass. And that drops off. You don't get as many very massive stars as you do not massive. So that, you may not exactly know what that initial mass function is, but you have some idea of how it works, and you can say that it's controlled by a distribution. Then there's epistemic uncertainty or incertitude. And that's where you don't know what's going on, but you can only guess that whatever you're interested in lies within some range, within some bounds. Okay. And so the question we wanted to ask is, well, how certain are we of the mass of the carbon-oxygen white dwarf prior to accretion? And that's question number one. I mentioned that the problem of steady accretion for a long time is difficult. So how do you do something like this? Well, okay. You get a student, you say, there's the MESA code, make some white dwarfs, all right? So MESA, I got to do a little bit of a sales job, although I'm not part of it, but it's modules for experiments in stellar astrophysics, 1D Lagrange hydrodynamics, solving fully coupled structure and composition equations for stars. If you take the graduate star course, you will see the equations of stellar evolution. This is how you solve it. Adaptive mesh, parallel. Independently usable models provide equations of state. One of my colleagues, for example, took the equation of state out, or took some of the burning, the nuclear reaction rates out of it, and was able to do stuff. And it's all publicly available. And the thing that's of interest beyond just the ability to make a white dwarf is it's many of the issues that we deal with in all of these astrophysical problems apply. It's a turbulent dynamical system, nonlinear, high-dimensional phase space. All these initial parameters, that's a dimension of the phase space. There's a wide range of energy and length scales. And then it has a discontinuous behavior. When you exceed a certain mass of something, it changes and stuff like that. So we thought this would be kind of fun to explore. So here, is the way we teach. This is from a textbook. This is the way we teach the evolution of a one solar mass star. Yeah, it's the cosmic perspective, I admit it. Which is a great book, but I shamelessly borrowed this. Here's our sun. It's going to sit on the main sequence for a long time. It goes up here. It becomes a red giant when it begins to burn hydrogen in a shell. It comes back down, it begins to burn helium, it goes up here, it becomes a double shell burning red giant, or we say it's on the asymptotic giant branch phase. It casts off its envelope, it comes down and becomes a white dwarf. All very, very simple. Now, if you run MESA, you don't see that. Depending on some of the parameters, and these are parameters in the winds, the mass loss there, you get funny behavior. You get multiple excursions through the giant phases, and sometimes you can do a little loop-the-loop over here. Okay. Question.
Where do they all start in the same place?
They all start, I think, down here, and then they go up giant, strange, asymptotic giant, strange, loop-the-loop, and then down here to a white dwarf.
And in all of that weird loop-the-loop stuff, how much time does it spend in all of that?
So it's pretty quick. It's 9-ish billion years on the main sequence, and then less than a year to do all this. MESA does the adaptive time stepping, and you just kind of see it suddenly start zooming around. That would be interesting to do a little bit better with this, but the point is that if you catch an observation in the middle of this process, you could see all kinds of different things. But then at the end, this is, sorry, I should have said that. This is an HR type diagram with the log of temperature versus luminosity over here. And the main sequence would be along here. It comes off, it goes up and down these giant bands. I should have explained that earlier, but Here's a lovely picture of it. You've got temperature and luminosity over here. And one of the things that we think is going on is that there could be some pulsational mass loss, so you're seeing deeper into it. That observing up here, there's no telling what you could get, but they're all fairly consistent, even though they may look very different at points in terms of the mass. And so we tasked the student with doing that, and that's what she accomplished in the summer, and we decided to go a little bit deeper into this. So the overall goal, as I've described, is we want to understand variations in the brightness. As you rightly asked, we're not at the Phillips relation yet. We're just turning the knob on how much nickel that you get. And the question is, does that follow from the properties of the progenitor white dwarf, like the central density that I showed you, that follows from properties of the host galaxy, its age or metallicity or something like that? So we wanted to look at the progenitor, and we wanted to treat MESA as a black box. That's something that you accept, but you don't necessarily know how it works. Now, in the case, yes, sir.
What you're looking for is also the width of the curve.
Correct, correct.
And which of the, I can see what affects brightness, but can you say what affects the width of the curve?
So I will say that the simplest assumption that not everybody agrees with is that the decay of nickel, the mass of the nickel sets the number of photons you're going to get to power the light curve, but it also sets the greatest source of opacity, so those photons take a longer time to get out. Now that's a very, very simplification, and not everybody agrees with that. But it's basically the fact that the more iron group stuff you get, the more opaque it is, so the photons take longer to get out. But, oh yeah, which is why we're just interested in how much nickel you make. It's like magnetic fields. We just so anyway, we wanted to treat the MESA code as a black box. Now, it's actually a crystal box, okay? The source is available and you can look at it, but we didn't want to lift the hood and start playing with it. We wanted to, this is a community code. It is a major advancement in the field of stellar astrophysics, in my not so humble opinion. And again, I'm not part of it, I'm just a fan. And man, years of work have gone into this. And we didn't want to start trying to tinker with it or trying to tune it to get what we thought would be the right answer. We wanted to say, all right, well, just taking this thing as a black box, it demonstrates nonlinear, possibly discontinuous behavior. So let's play with it from the point of view of something to test to see how certain these things are, how meaningful the results, and we don't want to try to reduce it. So there are multiple approaches you can take to uncertainty quantification. There are physical parameters, variability or aleatory uncertainties, as I mentioned, and then there are model parameters where there's an incertitude where you don't know the physics. And what we picked was the incertitude in the winds during the red giant branch and asymptotic giant branch phases, and they're controlled by two parameters. And just to start playing with this, we picked those two because that's where the funny behavior was, and we just wanted to evolve to the white dwarf. And so there are two formulations that are available in MESA that are temperature independent. We didn't want to introduce a third variable. The Reimers, and I'm not sure the pronunciation, is it Blukers? Does anybody know, like Frau Blucher, or is it... The students always said blocker, but Blucker. Okay, so it's like Frau Blucher. So anyway, these things are parameterized like this, where this is the Reimers and the Blucher, is that right? Thank you. Parameterization, where the eta R and the eta B are the fudge factors, where you just basically turn it up or down, and that is an incertitude. We do not have a good model for how these winds work. That means solving the problem of radiation hydrodynamics, which makes magnetic fields seem easy. Yes?
Okay, so given that some of the models have really interesting behavior, scrolling around.
Yeah.
How do you is there a way to cleanly, how do you operationally separate RGB and AGB if the models want to play there?
So we don't. I don't know how you would do that. That's what I'm saying. It's a mess. But the point is, what you're seeing, I think, is just material coming off and letting you see deeper in. It's a luminosity effect, and it's near the surface, but it turns out the masses don't change that drastically. Hendrik, you're sort of scowling. Is that okay? Okay. All right. Okay, so here are these two formulas, and the A to R and A to B, those are our incertitude. And here we have our epistemically uncertain inputs, and there can be n of them. We're only using 2, okay? And the first question you're going to say is, all right, Mr. Smarty Pants, why are you doing all this complicated stuff when you've only got 2 parameters? And the answer is to see if we can get it to work, because then when you're starting to do hundreds of parameters, you can actually solve the problem, which you can't do with just a brute force Monte Carlo approach. So we have these 2 methods that I'll define where we wrap our black box, which y is a function of x, where these are our uncertain inputs, and we run it capital N times. And the goal is, given an incertitude in these, what is the width of the output? What is our calculated bound on the output of this thing, which is going to be the mass of the white dwarf? So the simplest approach you can take is brute force. That could be a uniform, you just march through values of each parameter and calculate a grid. It could be a random sampling. All you know are the bounds. You know nothing about how the distribution occurs, so you can just take a random and see what you get. But the so-called curse of dimensionality gets you, and that is when you start going to, say, 100 parameters, you can't sample enough to get a good answer on it. It's just computationally not practical. So there are other methods that we apply, and I'm going to talk about these 2. Actually, these are the 2 that we applied. That of Cauchy-Deviates, which works for approximately linear functions. It's sort of like sweeping magnetic fields under the rug. We can sweep nonlinear functions under the rug too, and I'll show you how we do that. And these quadratic response surface models. So the real power of this is in the case of many uncertain parameters, not the 2. All right. So the Cauchy-Deviates method, that's based on a special property of the Cauchy distribution, which is also known as the Lorentz distribution, or the Bright-Wigner distribution, which I know some of the people in here have heard of that. And this is it. The probability goes as this thing, where this delta is a width, over delta over pi times the variable in question plus this delta squared over here. And the special property of this thing, and I know that this turns up in astrophysical reactions, and I've always wondered if this property is part of why we do the networks that we do, but I'll come back to that in the limit of infinite Allen time. But the key is that a linear combination of independently Cauchy distributed variables, that is, variables that obey this distribution, is also Cauchy distributed. And what that says is that for an approximately linear function, we can approximate the uncertainty of the model, the uncertainty in the model output, given those bounds on the parameters, which we associate with this delta for each of those guys. Now, this can be sort of a challenge because we're not assuming that there's a distribution given by this Cauchy. There's nothing physical about that. But what we're doing is using this linear property that the output is also Cauchy distributed just to see how the bounds change in that assumption. We're not assuming that it's physical. So this is what the Cauchy distribution looks like for several widths. You've got the 0.5 is fairly narrow and it's very steep. And the way we generate these, the deviates that go into the choices of the parameters in our suite of simulations is just the tangent of pi times a uniformly distributed random deviate minus a half. This is from 0 to 1, and just the tangent of pi times 0 to 1 minus a half gives you the Cauchy deviates. So if that's not crystal clear, I hope my image here will help, that you assume all of these input parameters behave like this you can treat linear, and then you get an output Cauchy distribution, and by measuring the width of that, that is an estimate on the uncertainty in your result. Okay. Now, it's especially cool because you can get a statistical measure of the uncertainty, that the standard deviation of this bound goes as its width times the square root of 2 over the number of simulations that you run. So if you want, well, I'll show it here. If you want a 95.5 2 sigma confidence in there, then you have to do at least 200 simulations to get within 20% at the 95% confidence level. Question over here. So,
Instead of like a Gaussian distribution.
Yeah, because this doesn't have a finite variance.
ooh. No, you're right. It doesn't have a finite variance. No, this is a very good question. I will show you in the paper where we discuss this, and I'm not dodging it, but you're right. It isn't just a Gaussian, but the reason why we're doing this is because this is the only distribution where you can assume that linear property that the output will also be of the same form, and then you can measure the thing from that. And the answer to your question as to how we do that, deal with that, is that you pick a random deviate, and you have to rescale the problem in each case for it. And I'll show you that in the paper. But that's a very insightful question, because you technically you could get some that are extreme, but that's right. And we had it actually took a long time for us to get comfortable with that. But you pick a deviate, and when you look at the second one, you scale the problem by the first, and that gets you the uncertainty, the distribution in the second one. And
But it also has right?
yeah, but that's what I'm saying. You've got to deal with those tails, and thank you. That's a very insightful question.
For a finite number of samples, nothing matters.
Well, but you have to. That's true, but you do have to take into account that these things, that there are fat tails. We'll come back to that. Here's a schematic. This is the output. You measure the full width half max, and then if you want the 2 sigma, that is 95.5% confidence, that say you're within, your statistical uncertainty is less than 20%, then you do 200 or more simulations to get it, and that's where that square root of n comes from. Okay, so that's method 1. Method 2 is the quadratic surface response model, and that can deal with the entire nonlinear problem of the black box. What you do is you run a suite of the simulations exploring the space, and then you construct a quadratic surface of your outputs, and from the max and min of that response surface, that gives you your bounds on the problem. And finding the max and min on this surface you construct is a constrained optimization problem, and strictly for convenience, we work on ellipses. And that means that you can write down the math to describe this thing fairly easily. It's much more difficult to try to do a rectangular region. That's why we choose the ellipse. And you're left with a choice of whether, if this is your bounds, where you've got 2 parameters, delta 1 and delta 2, here's the average value of the 2, and plus or minus the half of the width of the bounds. The question becomes, do you want to circumscribe or inscribe? And the answer is, if you play with it a little bit and realize that you're never going to have 2 that are extreme, if they're fairly centrally distributed, you can probably get away with this and go for a smaller calculation, but to be absolutely sure, you want to go up here. You also have to be very careful, and we found this out the hard way. It was actually kind of cool, because Scott Fersen, our UQ Jedi Master, we pointed out to him that we had problems physically in some of the range. So if you're doing the ellipse over here, and this is unphysical, you've got a problem there as well. And he had yet to run into a problem where that happened. So it's kind of nice that we helped improve the methodology. But anyway, you just perform a suite of simulations in this elliptical space, construct a response function, and then you yes, it does assume that they're independent. That's right. That's right. Then you've got to do something else. Wow, this is great. That's with me. Yeah, and I should have said, assuming they're independent, then indeed you're less likely to have 2 extreme ones, and that's why you can get away with it. So this is the form of our objective function that we do the fit to the surface. It's fairly simple, constant linear or linear and a nonlinear term. And then we put it all together and did a whole bunch of MESA simulations. So here's our initial brute force grid. And this is the color bar is the mass of the white dwarf, and this is in solar masses, so here's 0.5 and 0.58. And over here, this is the Brooker eta and the Reimers eta. And as you can see, you get in this limit up here, where these parameters got large, you get lower mass white dwarfs, which is very intuitive. If you've got a higher wind, you're going to blow more mass off. But one of the problems we ran into is that the thing didn't converge. These represent results where the MESA code did not converge. And the question becomes, how do you deal with that? Because remember, there are plenty of people that could tell us, oh yeah, we'll set this parameter or something to make it stable, but we're treating it as a black box. And we don't want to just try to get the answer. We want to see how we can do in that assumption. So here is a set of 200 random points, the same region of space where the Reimers and the Brooker eta. And I think this is actually, this may not be the same color scheme, but very, very obviously, if you don't see it in here, this obviously is nonlinear. The color changes drastically here, and here the mass of the white dwarf is on the third axis, and you can see that it is indeed a nonlinear function. And so what we did was break it into regions where it was fairly linear, and Don Wilcox came up with a clever way of doing the tiling. That's yet another optimization problem, and they're independent. And then within these quasi-linear spaces, we can get the output Cauchy distributed widths, and then tie that all together into one answer. And so we linearized it by just breaking it up into spaces that we thought were linear. Then with the quadratic surface response model, we just did a fit. These are the parameters that we got in this form. And then here, we did the math on the ellipse, but here just in our initial parameter space, the limits of these etas, this is the quadratic surface. And indeed, these guys do look fairly consistent, except here we've got a real fit to it. And it turns out that our bounds, I think, were largely on the corners, but maybe not all the time. And in the end, here are the results we got. So the Cauchy deviates at two different resolutions, the 1, 2, and 3 sigma. And if you remember, plus or minus 2 sigma is going to be bigger than plus or minus 1 sigma, and that's why these things increase. And then here's some results for the quadratic surface response models with choosing a smaller set of points. But I must be truthful here and tell you that I don't believe these results anymore. Sadly, the student graduated, and in working on the paper, we don't quite trust this and are going to repeat parts of the calculation. But I'm not trying to pull a fast one on you because this is what we got. I'm just not exactly sure if the simulations are all consistent. But this illustrates what we could get out of it. And indeed, I don't think I'm going to shock anybody to say that you get a white dwarf between roughly half of a solar mass. Question?
Yeah, I'm just curious. I mean, you say 1 or 2 sigma. So you start off with the parameters.
Yep. So
function which are having no
Yep.
finite variance, and you combine them, you say that you get another distribution, which is a function of all the parameters, and it has no finite variance. Now you have a result.
you can get, over your suite of simulations, you can get a statistical handle, a statistical uncertainty on that bound.
So what introduces the bound then? Everything else has no bound.
Well, when you say everything else has no bound, I mean you've got bounds on your input parameters, and then you send it through the suite of things through this black box, and then from the width of that Cauchy distribution you get out, that's how you get the bounds on your output. And what I'm saying is that within that, you can calculate a statistical uncertainty, a measure of the statistical uncertainty.
Are you using the fact that you have just running a finite number of simulations to get around the fact that Cauchy is not bounded?
Yes. Yes.
So if you ran more simulations, you would just get
Actually, it should get smaller because it goes as 1 over the square root of the number of simulations that you go. Now, you're going to ask the same question. Well, the distribution is not bounded, and we will look at the if not the paper, but the reference too. So.
But I think you can also declare an intermediate and confidence interval.
Yeah, no, that's what's good. That's what I'm saying. That for your number of things, this is your statistical sigma, your statistic, and then that gets you a confidence interval that you're at 95.5%, that you're in plus or you're within your output plus or minus delta y plus or minus 2 sigma is you're 95.5% confident of that. Oh, I'm really impressed with these questions, and I'm genuinely happy. This is very insightful, and I hope I can find answers. I mean, we were ready to submit, and then realized, wait a minute, we need to check something, and so, but I'll happily share, and we can resolve this. Okay, so what have we done? The quadratic surface model addresses the nonlinear function. The maximum and minimum of the surface are found, giving an estimate of the bounds. Finding the maximum and minimum of the surface is a constrained optimization. Oh, wait a minute, I read through this. So here is our quadratic. Here are our results. And to summarize, nothing surprising that white dwarfs from a 1 solar mass ZAM star are within the realm of 0.5 to 0.6 solar masses. Is quantified the effective results of some uncertainty to the input of the problem, modulo the good questions people have asked me. We saw the effects of resolution on the MESA models, and that's where we got into trouble because the input files, we ran into an issue with the Fortran read. So I don't think anything's going to drastically change. But I want to say that it actually is a lucky accident because in thinking about what resolution means in this problem, the higher you resolve, probably the larger your bounds are going to get because you're going to capture more features. And in a deeply nonlinear problem, you might catch some things. So I actually just want to say that if you ever do something like this, the resolution is not as simple as it seems because you're actually going to increase your bounds. We learned about some of the assumptions and the statistics of these UQ methods, including how to deal with the non-bounded distribution. And most importantly, we now have these tools that we're making freely available at Star Simulation Technologies for Research and Uncertainty Quantification, github.com starstruck. And you can get all of this stuff, including the tiling, if you're interested in it. And with that, we'll go to questions and discussion, and I will put up a bibliography and just say one thing, and that is that the paper is in prep. I did a short version of it for this AstroNum conference and submitted it. If the referees like it, that will be available. And if anybody really wants to get it, I can probably not get into too much trouble if I leave a copy of the paper. Comments would be cheerfully solicited. So, thank you very much.
Thanks, Alan. It's time for questions. There's a lot of talk, but go ahead.
How easy to expand your metric from 4 parameters?
That's the whole point. We haven't. Oh, sorry. The question was. Oh, I should have been doing that all along. The question was how hard is it to expand this to more parameters? And the answer is we haven't actually done this study, but the way we coded it, it should just be able to do it. And so the more parameters, that's where the real power comes in because you don't have to do such a huge sample.
For example,
How many
number of simulations you can run?
Well, so depending on what you're doing, the more the better, but with that statistical uncertainty that some people don't quite buy, if you run 200, then you're pretty sure that you're in a fifth of your bound, plus or minus.
So you alluded to looking at resolution and the impacts of resolution in the MESA simulations on this result.
Right.
So MESA has heuristics for deciding the resolution. And so any two simulations with two different parameters almost certainly don't have the same mesh.
Yes.
How do you...
Okay, so the question is, all right, Mr. Smarty Pants, you swept something under the rug. MESA chooses its own resolution, so two different simulations from slightly different parameters could be very, very different. And that's absolutely right. The way we looked at it was, we're telling MESA that this can be your minimum resolution or something like that, and then treating it that as its mesh adapts, it's consistent even though they're going to be different in places. So it's more like a limit on the possible resolution. That,
You mean you're treating the mesh refinement as sort of just another physical parameter that
it's part of the black box. Yeah, so the whole point of this was that we didn't want to start tinkering around and trying to make it work. We wanted to see how well it worked without going under the hood. So.
How is the number of points scaled?
Well, when you say the number of points, you mean the
Number of simulations.
well, yeah, so the question, thank you. The question is, how does the number of simulations you have to run scale with the number of parameters? And that's a good question. For the quadratic surface response model, you generally, that does a fit, that the more points you're going to get a better fit. So it's just a question of that. With the Cauchy deviates, that square root of n applies to each one, so it will go up, yes, yes. Sorry, I don't have a...
That's the first dimensionality.
Yes, but it will not scale as badly as if you were doing like a uniform sample, but it would take you a very, very long time to sample each one.
So you mean like if you had 50 inputs, it would be 25 times what you ran here. Each one would have, say, 200 points.
Yeah,
so
yeah.
Linear.
I think you could get away with it being linear. Yeah, yeah. These are all great questions. Yeah.
Well, certainly if you did something like Gaussian process model.
So that's another alternative. Yeah.
More or less, a handful of points to the power of, or a handful of points times the number of, like n, where n is your dimensionality, your inverse. It's not too bad. That's not.
Why don't you call it like Hendrik?
I didn't understand why the brute force method doesn't work.
So the question is,
100 parameters and you run 2,000 samples, you still get thousands of points in your final distribution. And as long as it doesn't get completely crazy.
well, so the question is, why doesn't the brute force work? And I wish I could remember the numbers, because Doug Swesty actually coded this up and tried it. And the answer is that if things are fairly centrally distributed, it just takes many, many, many more points to meaningfully sample all of the parameters than you can really, you really will be able to do, particularly if it's a fairly computationally expensive thing. It would take more than thousands of points. And
But I think the point is like it's an inefficient use of computational resources because you're oversampling where you don't care.
Yes.
You're undersampling where you do.
where you're undersampling when you're trying to find the bounds, which is the extrema.
So if you have the limit of what computation it would be trivial computationally.
Yeah, I think the brute force method would work in the limit that we could do.
Yeah, no, that's right. That's right. That's right. But if you're trying to do something like, say, in 3D, then this will win over that.
People do what we call for reaction rate networks with thousands of rates in 10,000 seconds.
That's entirely
Yeah, but how well we do.
Are there other questions? Right on. Well, let's make Al again.
Thank you.